Okay, hi everyone. My name's Erin, and I'm going to be talking about designs for practical, somewhat homomorphic encryption schemes based on the ring learning with rounding problem. And this is joint work with my lovely co-authors, of whom Anna and Rachel are here today, I think. Yes, hi. Cool. So yeah, thank you so much. So to begin with, work out how to use this. And then I'm just going to give a quick outline of what I'm talking about. So to begin with, I'm going to introduce the ring learning with rounding problem. I'm going to give a bit of a motivation for why we're considering it, an overview of the contributions of our work, and then I'm going to introduce the scheme that we're talking about. This is based on the ring learning with errors LPR scheme. LPR is essentially BFE. BFE is LPR with some homomorphic operations. So we're going to be considering this scheme first, and then we're going to introduce a learning with rounding variant of this. We're then going to sketch out how the security proof will look. I'm not going to prove anything live, so don't stress. And then we're going to evaluate in terms of comparison with BGV and some other related works, and then quick summary. Sorry. So first of all, what is ring learning with rounding? So before I can tell you about learning with rounding, I need to tell you about ring learning with errors. So if we let n be a power of 2, q a modulus, and consider the ring RQ, then our ring learning with errors sample is formed like this, A, B. Here, A is chosen randomly from RQ. S is the secret, which is usually chosen from a ternary distribution. And E is the error, which is chosen from a Gaussian distribution. And if we were to have many samples, then the S remains the same throughout, but the A would be sampled again each time, and also the E. So now we're going to consider how learning with rounding is different. So in learning with rounding, we have no Gaussian errors. This is a deterministic variant of ring learning with errors. And how we're going to achieve this, because we can't just get rid of the E altogether, is we're instead going to use a rounding operation on AS. So instead of adding a Gaussian in order to change the least significant bits, we're instead going to be sort of shaving them off instead, if everything is powers of 2. So yeah, this is how it looks. Everything else is the same, but we've just changed out the AS plus E for an AS rounded like this. So the rounding is mod P, and so just to conclude, this is deterministic, and so it doesn't need us to sample from Gaussian. The decision problem is the same as it was in RLWR. That is, are the pairs sampled from this distribution or from a uniform random? And the search problem is to find the secret, but we're going to be focusing on the decision variant. Okay, cool. So next up, we're just going to motivate why we're considering learning with rounding. So to start with, Gaussian sampling will be required to sample the errors in learning with errors. This can be quite expensive operation, and it can also be vulnerable to some side channel attacks. However, rounding, in contrast, is easier to implement. Like I said before, if everything is powers of 2, then rounding corresponds to dropping the least significant bits. There's also potential for improved bandwidth with smaller ciphertexts, even without all of the improvements that lots of libraries have applied. Several candidates in NIST have used learning with rounding, for example, Lizard, Round5, and Sabre. And it's not yet being considered for many advanced primitives, so this is quite an interesting space to think about. Okay, so now I'm just going to introduce sort of the two branches of our work. So we're introducing somewhat homomorphic encryption schemes based on ring learning with rounding. There are two main ways of constructing encryption from ring learning with errors. That's LPR and RegEv. And we show how to adapt both of these approaches to the ring learning with rounding world. We also give a security proof for each type, and we also give an RNS variant of each of them. We won't go into details on RNS today, but everything's in the paper, which will be on ePrint soon. So in order to get the security proof to go through, we adapt slightly the proofs that are already there. This involves quite some effort of introducing some variants of the problem. And today we're going to be talking about primarily the blue box version. So that's the LPR one, and then the RegEv one, the details are in the paper. We're also going to give some concrete parameter selection or comparison with BGV and other related work. Okay, so before we go on, we need to quickly look at the ring learning with errors, LPR style BFE. Oh my God, there's so many acronyms here, right? So basically, BFE is a scheme for doing FHE. Fully homomorphic encryption, guys. LPR is the particular style of doing BFE. And ring learning with errors is the regular problem we all know and love. So we're just going to talk about this version first, so we can then compare and contrast our learning with rounding version. Sorry, this does not change very fast. So the key generation process, we have our secret key, we have our public key, and our public key is formed like a ring learning with errors sample. Then we have our encryption process, which we apply to our message. U here is a uniform ternary polynomial. And encryption we can think of as masking by an RLWR sample. And we sort of scale the message to the higher order bits using the modulus Q. And then we can decrypt from here. Okay. And then the other thing that I want to introduce, so there's obviously lots of operations to go with it being fully homomorphic encryption, but we do have, like, the one that I want to particularly highlight is the multiplication. And you're thinking it's not the whole of multiplication. So this is just the first part of multiplication, where we've expanded to 3 parts. And after that, we could relinearize and get ourselves back down to a 2-element ciphertext. But the sort of nitty-gritty comes in this part, where you have the 3-element ciphertext. So this is why we're just thinking about this for now. Cool. Yeah, addition is easy. So the main bottleneck we have is this part of multiplication. And I also want to draw your attention to the fact that here, all the operations are implicitly modulo Q, because we have only one modulus. And this isn't a problem in the LWE world, but it is going to be a problem when we consider learning with rounding. Oh, we're considering learning with rounding. So I'm going to introduce now the learning with rounding scheme. So what you'll see is highlighted beautifully by Rachel in orange, the places where we had to change things in order to be a learning with rounding scheme. So the key generation, we have the secret key chosen from RR. We then have the public key, which is formed as a learning with rounding sample. We then have the encryption process. Okay. The ciphertext is formed by sampling U from the uniform distribution and setting like we see that. And in the decryption process, we need to be a little bit careful just to make sure that we are scaling everything to the right place so that we end up where we want to be. The other thing you'll notice is on the right side, we have to choose that PR equals Q squared. This is a parameter constraint for the security proof. But it kind of makes sense, since if we take powers of 2, then this sort of seems to fall out right. And it's also reasonable in terms of performance. Okay. So then we'll move on to the multiplication. So I've just refreshed the version that we had before from the previous type. And then we've got listed how we do it differently in learning with rounding setting. So in this situation, we have to scale a little differently. And this is in order to make sure that everything ends up in the right space. So choosing which space everything should go to is a very non-trivial task. And if you choose them like this, then everything seems to work out okay. And you end up with everything going where you want it to. You also don't have any noise terms, which you would be considering in the wrong ring. So if you consider a noise term in one particular ring, and then you're looking at it in another one, then potentially you can miss a bit and that part grows. And this has been a problem with like previous attempted constructions from this in this idea. So yeah, this is one way to fix it. The RegEv has another way to do it, but I'm not talking about that today. So then we also want to have provable security for our scheme. So I'm just going to briefly walk you through. It's the standard. We've got to do the learning with errors one before we can do the learning with rounding one. So the learning with errors scheme looks like this. We start off with our first hybrid. This is an honestly generated public key and ciphertext. So that's like the real in CPA game. Then we use decision ring learning with errors in order to say that the public key, remember it looked like a learning with errors sample, this is indistinguishable from a uniform public key. Then we're going to consider an honestly generated ciphertext. And then to get to the third hybrid, so the third hybrid is where everything is uniform, and the attacker has no information, we need to use the decision ring learning with errors problem in order to sort of get out of that, make sure that those CT looks like is indistinguishable from uniform. Okay, so how do we have to change this in the learning with rounding setting? So again, highlighted in orange are the things that are a little bit different. So we have an honestly generated public key and ciphertext. This is the NCPA game. And then we can use decision ring learning with rounding in the same way, like just using learning with rounding instead of learning with errors, because the public key is a learning with rounding sample. And we have our honestly generated ciphertext. And then from here, things are a little bit complicated. And they're complicated because the U is the same in both situations in hybrid 2. And so we've kind of got a learning with rounding problem. We've also kind of got, it's not just one learning with rounding, it's sort of with 3 different moduli, the R, Q, and P. So many moduli, so little time. So in order to fix, I'm briefly just going to discuss like why we need to do this. So yeah, at the top you can see here the 3 moduli ring learning with rounding problem. So this is exactly the version that we saw in the security proof, where you have your U's the same, and I hope I got all my R's and Q's and P's in the right place. I think it's good. Yeah, so this is distinguishing this particular form, which is what we had in our security proof, from uniform, all in the right place. And so the equivalent version in like having 2 versions of ring learning with rounding problem would be like having these 2, but these are not quite the same because the U's will be different. So yeah, it's a little bit different to just having 2 learning with rounding instances, but it's kind of a regular assumption with just a little unusual parameter setting going on. So yeah, we have a mapping lemma which we introduce in order to say that we can sort of map things from ring learning with rounding to ring learning with rounding, and also uniform to uniform. And the reason we want to do this is because this is going to help us when we're going through the security proof in order to make sure that we can reduce between the 3 moduli problem and the regular learning with rounding problem. So we also give, as our theorem 1, we give a reduction from 3 moduli ring learning with rounding to regular ring learning with rounding. So if ring learning with rounding is okay, then 3 moduli ring learning with rounding is also okay. So we've proved the in-CPA security of our scheme, relying only on the decisional ring learning with rounding assumption. Okay. So now the tables bit. So yeah, first of all, what we're going to do is we're going to do a sort of asymptotic comparison. Now, I've swept some things under the rug here because there's lots of P's, Q's, and R's, and I thought having so many different ones might be a little confusing. So bear in mind here that the LPR modulus R has the same size as the BFE modulus Q and the RegEv modulus Q also. I know. So yeah, here you can see like a sort of rough idea of what size the public key ciphertexts are. You can see the ciphertexts that we achieve are slightly smaller than the BFE ones, and the low ones are asymptotically larger. So this LWC 18 is a prior work which is based on the GSW construction. So rather than going via BFE, this work goes via GSW. Yeah, you can also see about the, if you compare the LPR style scheme, which is the one that we've been talking about mostly today, to BFE, you can see it's a little bit, the ciphertext size will be a little bit smaller. So asymptotically, things look good, but we want to see what's happening in practice. So this is quite tricky because a lot of people in this room have done some great work on their libraries, and their implementations of BFE are really good and efficient in so many optimizations. And so it's a little bit tricky to compare kind of a new scheme to this. So what we decided to go for was a sort of concrete comparison with BFE. So we're comparing ciphertext sizes between our scheme and BFE. So the methodology for this is to find parameter sets with minimal ciphertext size such that we can achieve 128 bits of security, and we can also support a sort of tree-shaped arithmetic circuit with depth L while having a correct decryption. And each level here is 8 additions and 1 multiplication. Okay, so then we're going to see what the actual ciphertext sizes are. So these are the minimal ciphertext sizes that in kilobytes that support multiplicative depth L with plaintext modulus T equals 3. And you don't have to read all the numbers. Basically, I want you to take away that in most cases, the LPR-like scheme is providing a smaller ciphertext than BFE. And this doesn't just work for plaintext modulus T equals 3. It works for some other plaintext moduli. So in this case, T equals 2 to the 8. You can see the same sort of pattern applies. We tried this for a range of plaintext moduli, including 2 to the 16, 2 to the 32, and 2 to the 16 plus 1, 2 to the 32 plus 1. A similar sort of pattern is observed in all these cases. Great. So now quickly to summarize. What we did is we designed 2 somewhat homomorphic encryption schemes based on the ring learning with rounding problem. This is the RegEv style and the LPR style. We've demonstrated that building BFV-like schemes is possible from ring learning with rounding, which was not previously thought so. That's why people were going via GSW. We also provide security proofs for both schemes. We show that RNS variance can be achieved. I didn't go through this today. We also improve ciphertext sizes compared to BFV. And the parameter sizes are comparable to BFE. So the possible next steps, like I mentioned, all of these amazing library optimizations, it would be really cool if we were able to sort of integrate this into a library, take advantage of some of the amazing work that people are doing, and see how that looks. I think like learning with rounding, like I mentioned at the beginning, is quite an underexplored area, so it might be interesting to build other things from learning with rounding. There's also different applications. So, for example, given that the ciphertext size is a little smaller, some applications such as private set intersection, where lots of ciphertexts are exchanged, could be a useful thing to consider. And also, maybe your cool idea here. Perhaps you have something that you think might work, and you want to tell me about it, in which case, do come find us, and I'd love to talk about it. Great, so thank you so much. This is my details. The paper will be on ePrint soon. Thank you very much for your time.
Thank you for your presentation. As a hardware designer, I'm really a fan of learning with rounding.
Thank you.
Questions?
Just want to explore the definition of the roundings that you have in your slides. Like you mentioned, rounding x to pq is essentially something like rounding p multiply x over q. Is this a true, or did I misunderstood that?
Yeah, so, I don't really, yes.
That is correct. Okay. So if that's the case, so you have a multiplication operation and then a division operation to do the rounding. And from your experience, is this faster than sampling a Gaussian point?
Yeah, so one of the things that sort of in a Gaussian, applying a Gaussian instead, you have to sample the Gaussian. Whereas if you're in the situation where you have powers of 2, then the rounding process just it implies you're basically cutting off the least significant bits.
But
so
after
this is
multiplying and dividing, or no? Like this
Yes.
is after the multiplication and division?
Yes.
So my question is, so I agree with the cutting off bits, but I just want to explore if multiply then divide is better than sampling. This is my main question.
I think because you're multiplying,
Multiplying with the power of 2 is shift to the left, and division by power of 2 is trimming the bits, so we don't do the multiplications and the divisions.
yes.
Yes.
Sorry, that was not clear. Yeah, so we most often people are choosing P and Q powers of
So
2.
one question from the back.
Yeah, so theoretically, learning with rounding is equivalent to learning with errors, with uniform errors over a small bounded interval. And so one of the motivations for using Gaussian errors is that they allow better, tighter error growth analysis in homomorphic encryption. And it's not just security. So I wanted to ask if you looked into the impact of using learning with errors in terms of error growth, learning with rounding in FHE with respect to error growth, either by theoretical bounds or heuristic bounds.
Okay, so the question is, I think, did we do sort of noise analysis and think about how the errors are going to grow in the learning with rounding case as well as the learning with errors case? So yes, we did. We have a noise analysis for the learning with rounding case. We found that the noise growth looks fairly similar to that of BFE. So the noise formulas don't hold too many scary surprises. Thank you.
So when you did your security analysis, you just basically assumed that LWR is kind of like LWE in the same way that Martin did that in his paper where he analysed all the NIST candidates. You didn't actually use the theoretical reductions between LWR and LWE, which kind of then have this kind of quadratic explosion in the error in the advantages. Yeah.
Yeah. So I'm gonna say I didn't write the security proof, which feels like a cop-out, but I'm gonna answer as best I can, and then we'll see how we go, okay? So, yeah, so basically the reduction that we give is from the learning to learning with rounding, and there is a reduction then from learning with rounding to learning with errors. So we did the learning to learning with rounding bit, and yeah, so. Oh. Yeah. Yeah. Sorry.
Okay.
Thanks, Anna. I didn't understand the question properly.
Okay.
Thank you.
We can continue that discussion also during lunch.
Amazing, yeah.
Let's thank the speaker again. And we go to the next presentation.
Thank you so much, everyone.
Thank you.